As large language models are deployed for complex tasks like document analysis and code-based comprehension, the demand for massive context windows has grown exponentially. However, expanding the context window of standard transformers presents a severe mathematical and physical hurdle. Autoregressive self-attention scales quadratically with sequence length, making the memory footprint of the key-value cache massive. Furthermore, standard positional encodings, such as absolute embeddings or even rotary position embeddings, fail to extrapolate to sequences longer than those seen during training. When a model trained on a length of 4,000 tokens receives an input of 8,000 tokens, the dot product attention scores diverge, causing catastrophic performance collapse. How do we scale context windows without retraining models from scratch? Attention with linear biases, or ALiBi, introduced by Press and colleagues, offers an elegant, zero-overhead solution by completely bypassing positional embeddings in the network. Instead of adding positional vectors to queries and keys, ALiBi penalizes the attention scores directly. For query index I and key j, a constant penalty proportional to their relative distance, absolute I minus j, is subtracted from the dot product of query and key. This penalty is scaled by a head-specific slope m. For a model with h heads, the slopes are set as a geometric progression. This simple mathematical bias naturally guides the model to focus on local context while allowing it to extrapolate gracefully to arbitrarily long sequences during inference, requiring zero extra training. While ALiBi works well by biasing attention locally, many modern models rely on rotary position embeddings, which encode relative positions geometrically. To scale RoPE-based models, standard linear interpolation divides the positional frequency by a constant factor, but this dilutes high-frequency details, ruining local structure. YaRN, or yet another rope extension, solves this by implementing a multi-band scaling strategy. Based on the neural tangent kernel, or NTK, YaRN separates the dimensions of rope into 3 distinct bands based on wavelength. High-frequency dimensions are left completely untouched to preserve local resolution. Low-frequency dimensions are fully interpolated to scale the global coordinate space. Intermediate dimensions are smoothly transitioned using a specialized interpolation function, achieving state-of-the-art context extension up to 100,000 tokens. A fundamental limitation of all traditional positional methods is that they measure distance in raw token counts, which is highly sensitive to tokenization quirks and padding. Context-Position Embeddings, or CoPE, introduced by Bader and colleagues, reimagines positions by measuring distance in terms of semantic units, such as words, sentences, or paragraphs, rather than raw tokens. CoPE computes a gate value for each token that determines whether it should increment the positional count. The position of key j relative to query I is defined as the sum of these gate values for all tokens in between. This dynamically scales positions based on actual content density rather than arbitrary token boundaries, allowing the model to generalize perfectly across varying text formatting. By co-designing hardware-aware caching with mathematically rigorous position interpolation, modern architectures have broken the context barrier, scaling from thousands of tokens to over 1 million. Whether through the static local biases of ALiBi, the multi-band geometric interpolation of YaRN, or the dynamic content-dependent gating of CoPE, transformers can now retain perfect retrieval resolution across vast horizons. This optimization of positional representation forms the core of modern long-context language modeling. To keep exploring the elegant mathematics and hardware mechanics driving modern AI, subscribe to Gemini 3.5 Flash Model. Let's keep optimizing the future of computation.